Okay, hello again, YouTube. Today, we're going to cover a method of solving for differential equations in ODE, and it's called variations of parameters. So, in the last video, we covered how to solve for differential equations that look like this, where we had like cosine of t on the right-hand side as our g of t, but the thing is, for the method of undetermined coefficients, g of t must come in the form of e to the t, sine of t, cosine of t, e to the t, sine of t, or e to the t, cosine of t. And then you can just like multiply t to the n power, but it must come in this form. Otherwise, it is incompatible with the undetermined coefficients. So, if you want to solve for a differential equation with something like y double prime plus 9y prime plus 9y equals tangent of t, or secant of t, well, you have to use variations of parameters. So, in the variation of parameters, let's say you're given a nth order differential equation, so like y to the nth derivative plus dot 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 something. I'll just put like h of t y equals g of t. So you are going to generate n numbers of solutions. So your solutions will look something like this. So you'll have an n number of solutions given an nth order differential equation. And this uses something known as the superposition principle, where if any one of these are solutions, the sum of them will also be a solution for this differential equation. So how exactly do we find what u and y is in this formula? Well, let's find out. Okay, so what exactly does this u of t and this y of t exactly mean? Well, y of t here, the little y, is the characteristic solution of the differential equation. So let's say we have a simpler differential equation, y double prime plus 4y prime plus 4y equals to tangent of t. Well, we already know how to find the characteristic solution. That's r squared plus 4r plus 4, set that equal to 0, we'll get r equals negative 2 of multiplicity 2. So the solutions we'll generate are y1 of t equals to e to the negative 2t, because negative 2 is our solution to the characteristic solution, and our y2 of t is going to be, well, since it's multiplicity 2, we multiply an extra t, we get t times e to the negative 2t power. So we got y of t out of the way. Now, what is u of t? Okay, so u of t requires a more complex formula, where our formula for u of t, or rather u of I of t, since y of t is the sum of all these u1s, y1s, like just un, yn. So I'll just call it ui of t is equal to the integral of Wronskian I of t times g of t over Wronskian of t dt. And what does Wronskian have to do with anything? Or, sorry, rather, where are you taking the Wronskian of? Well, if we look at these two solutions, these are the functions that we'll be taking the Wronskian of. So let's start off with Wronskian I of t. So what Wronskian I of t is telling you is, let's say you had like the Wronskian 1 of t. Well, they would be asking you to put 0, 1 in place of what would be on the first column, and then you would put what you would normally put on the second column. So we have t e to the negative 2t as our first row second column entry, and then we would put its derivative right below it. So that's e to the negative 2t minus 2t e to the negative 2t. And then we take its determinant, which is negative t e to the negative 2t. So that would be our first Wronskian. So what Wronskian I of t is saying is that whatever number you plug in for I, you just replace that number column with a 0, 1. Or let's say you had a third order differential equation, well, you would replace that column with 0, 0, 1. So basically your last row entry for that column would be 1, and then everything above it would be 0. So let's say we want to find the second Wronskian. Well, that would be the determinant of e to the negative 2t, its derivative below it, negative 2 times e to the negative 2t, replace the second column with 0 and 1. So if you find the determinant, it's just e to the negative 2t. And then g of t, we already know it's right here. So let's just label tangent of t with g of t. And then the overall Wronskian is what I call it, or just the Wronskian. Well, that's w of t equals to the determinant of, sorry, bad placement. So the Wronskian of t is equal to the determinant of just the solutions without replacing any row with 0, 1. So it would be this. Okay, I'm not good at drawing straight lines and placing numbers and stuff, but you get what I'm trying to say. So w of t equals determinant, so that's equal to e to the negative 2t times e negative 2t minus 2t e to the negative 2t minus t e to the negative 2t times negative 2e to the negative 2t. And then if you add this up, because this is AD minus BC, you get e to the negative 4t minus 2t e to the negative 4t plus 2t e to the negative 4t. These two cancel each other out, and we're just left with e to the negative 4t as our overall Wronskian. Okay, so now that we got all that Wronskian stuff out of the way, we can plug it into the formula. So we know u1 of t is equal to the integral of first Wronskian, so Wronskian 1 of t, g of t over overall Wronskian, or sorry, just write that better. So that's equal to the integral of negative 2 e to the negative 2t times tangent of t over e to the negative 4t dt. That's equal to the integral of negative t e to the 2t tangent of t dt. Now, our first solution consists of u1 of t times y1 of t. So what we have to do is take this and multiply that here. So our first solution is equal to e to the negative 2t times the integral of negative t e to the 2t tangent of t dt. And I know I can't evaluate that integral. It's too complex for me to be able to integrate. There's no calculus simple techniques to integrate this, so I'm just going to leave it at that. Okay, now on to our second solution. So we know that u2 of t equals second Wronskian, integral of second Wronskian of t, g of t over Wronskian of t dt. So that's equal to the integral of, well, we can plug in that e to the negative 2t times tangent of t over overall Wronskian of t, so that's e to the negative 4t. So that would, dt. So that would equal e to the 2t tangent of t, the integral of that. So now we need to multiply that by y2 of t, so u2 of t times y2 of t is just equal to this times that. So it would be t e to the negative 2t times integral of e to 2t tangent of t dt. So we know y2 t. Well, actually, no, it's right here. So our solution, our overall solution from the variation of parameters would be big Y of t is equal to y1 of t plus y2 of t. And that would equal e to the negative 2t times integral negative t e to the 2t tangent of t dt plus what we have here. So that's t e to the negative 2t integral of e to the 2t tangent of t dt. And no, I'm not going to try to sum it all up and simplify it. It's too complex of an integral for introductory calculus techniques. So I'm just going to leave it at that. This is our solution to this using variation of parameters.